All right, this is going to be kind of a quick and dirty video on volumes with the method of disks. I couldn't fit all that text here, so I just wrote that. And the reason I do this is because it's I think a lot of the textbooks and other videos miss the mark a little bit. So this is, I'm not going to show anything new, but I'm going to describe it in a little different way, maybe with a little different approach. And so you may wonder, why are we so concerned about finding the volume of something using this method of disks? All right. So let me go into full screen here, and I'll kind of show you what I mean. The textbook and all the other videos, you will see they're all about this. You know, you've got some curve like this, and then, you know, let's say it's y equals x. Right, and so this is x and y, and we're going to take this thing and we're going to revolve it around the x-axis. All right. Well, if I take this line, say from here to here, and I revolve it around the x-axis, what shape is that going to make? Well, it's going to, this line will still be there. It's going to revolve all the way down to here, and then it's going to revolve like that, and so this looks something like a cone. Okay, so revolve y equals x to make a cone, and then find the volume. Right, that's the big challenge, is find the volume. Right, now, the obvious question may be, well, we have a formula for a cone, right? We know that the volume of a cone, I think it works out to be 1/3 of the area of the base times the height, something like that. And so that works out to be 1/3 times pi times the radius squared times the height. Right, this is the volume of a cone. So why do we bother finding the volume of a cone using all this? Right. Well, my question for you is, and I'll put this in, I guess I'll leave it in red, is, and I'm going to be a little unprofessional, but where the hell does this come from? Right? Because your geometry teacher told you that, or your physics teacher told you that, or somebody told you, you saw it online, right? Well, without really knowing where this formula comes from, I propose that it's not really worth very much. All right, now, a formula that I do know a little bit better, and that I actually believe, is the volume of a disk. Volume of disk. Right. Well, I know that the area of a disk is area equals, what is that, pi r squared. That's the area of a circle. And so if I make that into a disk, so I make it three-dimensional, so the volume equals pi r squared times the height. Right? So this little dimension here is radius, and that little dimension there is the height. Right? And so we go pi r squared h, and that gives me the volume of a disk. Right? We take a certain area, we extrude it up, we go up and down to this area, and by definition, that is what volume is. All right. Now the question is, here, well, let's call it a problem. I like to solve problems. The problem is, a disk looks nothing like a cone. Right? They're not the same. And so my original problem is, I've got a cone. What is the volume of this cone? How does a disk help me with that? All right? So that's a perfectly valid question. So I'm going to open up another little window here, and admittedly I couldn't figure out how to make this mathematical window bigger, but here we go. So This is done with the software Mathematica, a very powerful tool. If you ever get a chance to use it, you should learn how to do this. If you're going, certainly if you're going into the physical sciences. So here's this line y equals x, right? Just a sloped line like that. And then if I rotate this line y equals x all the way around, right? What does that make? It makes a cone. Okay, so here's a cone, right? But I don't know the formula for a cone, right? I do know the formula, however. I'm going to back this away from there again. So there's part of our cone. I do know the formula, however, for a disk, right? And this is kind of a fat disk. But what's the volume of this one fat disk? Well, it's pi r squared h, right? I find the area of this little part of it here, and I make it h. Now, you're thinking, this is silly, right? We still have the same problem. This disk is nothing like this cone. It has kind of the same radius here and kind of the same height there, but it's still not very good. But what if instead of one disk, we use two disks? Well, what's going on here? There we go, or there's two disks there, right? Now all of a sudden, okay, it's believable that this cone and these two disks have, well, at least they're closer in volume, but it's still not a very good approximation. What if instead of two I had a bunch? Okay, now we're getting somewhere. Now this stack of coins and this cone are approaching the same volume, right? Well, you can see where this is going. What if I go all the way up to 20 disks? Now, as I rotate this thing around, the blue and the red, let's back the red out of there. I mean, this is definitely starting to look like a cone. I mean, it's still not perfect. Obviously, the blue coins that are stacked up here are going to be less than the original cone. But what if I go all the way up to 30 cones? Now we're getting really close. Of course, we see where this is going. What if I used 100? What if I used 1,000? What if I used 1,000,000? Right? Now we're getting there. If I use 1,000,000 little disks all stacked up, and I add up all those disks, I'm going to get pretty darn close to the original volume of my cone. Well, what we do is use the limit as the number of disks goes to infinity, right? And then I will get exactly the volume of the cone, but I'm using only the volume of disks to get there. But I've got to add them all up, and each one is different, so this could be a real hassle. So let's go back to this thing here. Full screen, and we'll go to the next page. Or maybe I can fit it down here. So I've got, am I still in blue? I've got my original function. Well, I've got my original cone. And my cone starts with a line that goes like this. And for now I'm going to say y equals x. And I'm going to split it up into a bunch of little disks. I'm going to rotate this around, right? So it gets rotated around like that. And I'm going to make it into a bunch of little disks. Each disk starts with this little thing here, right? So I've got a bunch of those really thin little disks. Well, first of all, I've got to say, what is the volume of, and this is where it's absolutely critical. Where's my pen here? Get rid of that. Go back to my pen. Absolutely critical here. Right, this is the most important step that unfortunately I think most people miss, and that's what I'm going to spend some time. What is the volume of one of my disks? Okay, well, to do that, I'm going to draw a picture of one of my disks. Here's our same original profile. This is y, this is x, and then I draw this line that goes up like this. That's y equals x. And so one of my little disks that I'm going to stack up in here looks like this. I'll do it in orange because orange is one of my favorite colors, and it's so important that here's one of my disks. gets rotated down like that, and then the thickness of my disk goes like this. All right, that's one of many, 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 many disks that I'm going to add up. So this is, I'm going to just call this a typical disk. And it is critical to know the volume equals what, right? Well, I know the volume equals, I know the area of a disk, right? The definition is the area of the base times the height. So it's the area of the base times the height, right? Well, here's my height. That's the easy one. That's height. The radius of this, or the base is pi r squared. Pi r squared, and then I still have the height. What's the radius? Well, the radius here is y, right? Now, I could draw the radius. I could draw from the center of my disk. I could draw my radius here. There's a radius. I could draw a radius here. That's a radius. I could draw my radius here. That's a radius. But my radius, if I draw it like that, my radius is y, right? So the volume of my disk becomes pi times y squared times h. But I know that the volume of this is, I know that y equals x. Well, I'm going to make a little note down here because I can't really draw across there well. Because y equals r. I also know that I can rewrite this as pi times x squared times h. Why can I do that? Because my function says y equals x. Right. Now here's the kicker, is what is the height, right? Well, the height is going to be, right, I'm going to make these smaller and smaller and smaller and smaller, this little h, because I want to fit 1,000,000 of these disks, and I could fit maybe 20 of these in, but I want 1,000,000 of them, so I got to make this h really, really small, so that becomes dx. Right? So this is the volume of one disk. And this is absolutely critical to know. That gets a red box. All right. The volume of one disk, right? But I don't know, I don't want the volume of just one of my disks, right? I want all of my disks. I kind of picked, yeah, it's kind of a funny looking red. So I want all of the disks. Right? The sum of all disks. Right? And so how do I get the sum? Oh yeah, this thing here. It looks like an S for a reason, right? It's the sum of all the disks. So it's the sum of all my individual disks, which is this guy here, which is pi times x squared times dx. This is one disk. That's my integrand, right? And all of the disks become this. Right? All of the disks. Okay, well, let's just be kind of mathy here and say I'm going to go from, the limits of this thing are going to go from 0 all the way to just some arbitrary, call that b, right? Call this a equals 0. And so if we go all the way to b, we're going to integrate this from 0 to some random number b. Okay. On the next page, let's investigate this. So we're going to go from 0 to b of pi x squared dx. All right, so next page. I'm going to do the integral from 0 to b of pi x squared dx. Well, I can pull the pi out of there because that's a constant. Let's make a note of that. All right, so I can pull that out. So I'm going to rewrite this as pi times the integral from 0 to b of x squared dx. Now, we know from the fundamental theorem of calculus that this equals pi times the antiderivative of x squared, which is x cubed over 3. And that's going to go from 0 to b. Right? That's from the fundamental theorem. We use the antiderivative. Fundamental theorem of calculus. Antiderivative. Okay. And then so we can substitute our values in, substitute our limits in. So it becomes pi times b cubed over 3 times, let's see, 0 cubed over, or minus 0 cubed over 3, which is, let's see, that just works out to be pi times b cubed over 3. Or another way to write that equals 1/3 pi b cubed. All right, now I'm going to write that one more time in a little different way. It works out to be 1/3 pi b squared times b. Now why would I write it like that? 1/3 pi b squared times b. That sounds a little bit familiar. Let's take a look back here. What is the height of our cone? B. What is the radius of our cone? B. So this equals pi r squared h, or no, we got to go back one more. The volume of the cone, 1/3 pi r squared h. The radius was b and the height was b, so it's 1/3 pi b cubed, or pi b cubed over 3. Right? That's where that formula comes from, right? Is calculus. So that's that. Now, you still may be convinced or unconvinced that we've got a formula for a cone. Why are we doing all this calculus, right? And there's something you said for being lazy. All right, fine. So what if I gave you a different shape, and I said this is my y-axis, and this is my x-axis, and I'm going to draw y equals square root of x. Looks something like that. Right? I'm going to do that from, let's say, go from 0 to, how about something convenient like, I don't know, 16? Right? And I'm going to revolve this guy around the x-axis. Right, so it becomes this shape here. Let's see if I can draw this. Like that. And then the other side is going to go down like this. Right. Now, I don't know what shape this is. We can call it a bullet, I guess. Bullet-like shape, maybe a tipped over wine glass, maybe a That's about all I got. Bullet or tipped over wine glass. Flower, tulip, whatever. Well, I dare you to look in your old geometry book and find a formula for the volume of a tipped over wine glass or the volume of a bullet where the profile equals the square root of x. All right, so what are we going to do? We're going to break this down into little discs. So here's one little disc, the top of my little disc, and it's kind of going to go down like that. And then here's the other edge of the little disc. It's going to go like that, and then this. Right. Well, so what's the volume of one disc? Volume of one disc. It's V equals, what is it, pi r squared h? Pi r squared h. What's my h going to be here? All right, well, let's draw h up here. That's the height of my disk. It's like a little coin, right? That's dx. And what's my radius going to be? I could draw my radius anywhere here, but I'm going to draw my radius right here. So I know that, so where's my stylus? I'm having trouble. There it is. So my radius still equals y, height equals dx, but this time my y value is actually the same as the square root of x. Lost my stylus, and there it is. Okay. So my radius equals y, which equals the square root of x this time. And so one of my disks is pi r squared h, so that becomes pi times the square root of x squared times dx, which equals, oh, that's convenient. I didn't really mean to do that, but that works out nicely. Pi times square root of x squared is just x dx. Right, so if I want all my disks, go back to orange, volume of all my disks, that equals V equals the sum, right? Oh, yeah, that symbol, right? It looks like an S for a reason. From 0 to 16. That's all the values of x that I'm going to use. And, you know, the value of x, the position of my disk, is going to go from 0 all the way to 16. Of, let's see, I'm going to put the pi out. I'll leave the pi in here right now. Pi x dx, which equals, pull the pi out, pi times the integral from 0 to 16 of pi times, or pi is out of there, x dx. That's an easy integral to do. We'll do the antiderivative again. So it's pi times the antiderivative, which is simply x squared over 2, from 0 to 16. Right, so it's 256 over 2 minus 0 over 2, so that's 128. We'll just go up there. Equals 128 pi units cubed. Right? There's no formula for that. We have to use disks. But the absolutely critical... Okay, so first let me show you what I find is just a travesty. This is a travesty here. Right? They're saying, oh, yeah, right? The volume for disk by rotation of... Oh, and here's the same one. Okay, I also didn't mean to do that. But whatever. Right? The volume for disk for rotation about the x-axis. And they give you this nice, neat little formula. 0 from a to b of ax dx, which is pi times the radius function of x squared times dx. Yeah, great, right? But a monkey can plug numbers into a formula. What are you really doing here? It's important, it's critical to know what you're really doing, right? And that is you're finding the volume of one disk based on your knowledge of geometry and based on the shape and the constraints of the problem. And then you're going to find the volume of all the disks by integrating from 0 to 16, right? From one end of the bullet to the other end of the bullet, right? Please, please, please don't use these formulas, right? Don't use this formula, right? It'll become a crutch and you'll completely lose the point of doing calculus. Understand that this is just one of these disks, and we're going to find the volume of one disk first, and then we'll get the volume for all of them by integrating. All right. I hope you got something out of this. I hope it cleared things up a little bit. Con, Krista, Patrick, they all have tons of examples. Mr. Taru, Professor Rob, they've all got a lot of examples, but I require you to understand what's actually happening. That's it. Enjoy. Talk to you soon.